So hi everyone, I'm Eric, and today I'm going to present the work I've been doing with my collaborators at UCSD. So the name is Laurel, Unblocking Automated Verification with Large Language Model. But before diving deep into what we did, I want to come back on why automated verification and why not like proof assistant, or like what are the differences and what does it exist. And so for that, I'm not going to use what I did, but mostly what was written in the Dafny paper, which is like there is like two ends of the spectrum. There's like on one side is like proof assistants with lean, that like or like COC that use tactics and that like a lot of manual efforts, and potentially you need to have a decent amount of knowledge in formal methods. And on the other side, there's Dafny that like offloads a lot of the proof to the SMT solver, but we stayed like kind of at the program level. And so for that, we have like the automation through SMT solver. But what Rustan didn't talk about is that now we have actually another kind of automation that is taking over. I don't know if you heard about it, but it's called AI. And so we kind of need to think about like how is this changing this paradigm? Like, is it making like, for example, theorem prover like easier to use than automated verifier? And how can we apply AI to both of this technology? And so today I'm going to focus on automatic verifiers and Dafny and how can we apply AI to it. But before that, we actually need to understand what's the automation that is already available in Dafny. And so for those who were at my talk yesterday, I had a user study where like people were complaining about Dafny or saying the good points about it, and they had this method here that was like, okay, I want to verify this method that applies a discount on a number X with a certain percentage, and I just want to show that my result will be positive because I don't want to have a negative price and lose money. So pretty important for them and pretty straightforward to implement, but somehow difficult to verify. And why? When we look at the code, it's straightforward, it looks correct. However, does it verify? It does not. Like Dafny tells you, like, yeah, I cannot verify that the result is positive. And so as I said yesterday, what you do is you add assertions to help the SMT solver and help Dafny and guide it towards like the goal that is proving that the result is positive. And so what you need here is this assertion that says like that the multiplication on two positive terms results in something positive. And so this is kind of surprising for a programmer that has no formal methods. But however, especially when we say, oh, it's automated, why do I need to add this assertion if it's automated? But for someone that knows formal method and actually read the paper that I referenced before on Dafny, well, Rustan was well aware of this. Automatic, this is not to say effortless. For it really usually requires interaction at the level of the program being analyzed. And so what's interesting here is like, well, Rustan, what he was saying is like, I will ask you maybe to add annotation or facts about things that are in the program. And indeed, like here in the assertion, we're talking about X and factors that are like a variable that we can see clearly in the program. So, okay, this is great, but users still complain about this. And now we have AI, so obviously we can do better, right? And so the idea is like, we can push this automation further by generating this assertion automatically. And so and for the problem to work, for the solution to work, I want to make the problem simple. And so for this, I'm going to base myself on observation made on real world code and on code base that are available online. And so the first one is assertions in Dafny are the most used annotation, 5 to 11% of line of code. Forget about loop invariance, they're a small part of the annotation. They're like less than 1%. Why? Because when you go like higher in your proof, you're not in imperative programming anymore, and hence you don't need loop invariance. The second thing is kind of like super intuitive. Well, you rarely start a proof from scratch. Yes, you're going to start it at some point, but your proof, like you're going to have multiple steps, and so like these assertions, you might have to like you might have like some backload proof that you already work on, and also like there are a ton of proof available that you can look at. And so now that we have a problem that is kind of simple, let's apply to a LLM to it and see if it actually works. And so like the question is like, can we fix this proof by inserting one assertion? So like we have a program like the one I presented before that just need one assertion, and we need to we ask the LLM to find it and see if it works. And so for this, we use this benchmark from actual real code that is deployed, like the standard library in Dafny, CDAR, that is a notation library, and Dafny AVMC, that is a random number generator. And I want to emphasize that this code is a non-trivial Dafny code. It is not like some like benchmark that is made up. It's like actually code that was written to be deployed. And so what we see in this graph is actually when we just ask this question and we ask to generate the assertion, we get a really low success rate, like less than 10%. And when we're a bit smarter, we say like, oh, look, we had an error message before. Can we just give it to the LLM? Well, we only get up to 15%. And well, if the LLM can generate like only 15% of the time the good assertion, well, nobody is going to use it, right? So good news, we still have some work to do. But what we can know now is like LLM do not work out of the box for assertion generation. So we need to actually be smarter about it. And so the question next is like, why don't they work? Why is it not working? And so here I have a lemma. You don't need to understand what this lemma does, and actually you can't because there's a bunch of dots. But what you can see is that there is an if and else case, and the assertion is needed in the else case. This is for showing termination and for helping the SNP to show termination, but the assertion is needed here and not in the if case. And so the question is, where does the LLM generate the assertion when you just ask it to add an assertion, right? Well, not really where we want. In the baseline case that I showed you, like it goes between like 0 and 15 lines far from where the assertion should be, and the error is a bit better, but still not great. And this is something kind of really precise, because if you offset by 1 line, you might be in a different path of your program, and the assertion might be useless. So okay, what we learn is like, unlike users, LLMs struggle to actually find the correct location for assertion. So, well, the solution seems simple. Can we help the LLM with the location? Well, we have the error message, and as and with like some kind of algorithm, we can actually provide a placeholder to tell, based on the error message, where should the assertion go. And so we can now provide a placeholder to allow the LLM to focus on the assertion. And what I mean by that is like now the LLM will actually not think of the token in terms of like both a placement where the assertion should go, but just like now the assertion should go there. These are the tokens and the assertion that will generate for this position instead of others. So we did this. How does it work? Well, it works pretty well. Like what we see is a 2-time improvement versus just giving the error message. And in this one, we don't even give the error message. We just give the placement and we ask to generate the assertion. So great. The second thing that is also great is that on the first try, we actually get 25%, which is good because LLM are actually quite expensive to run. But 25%, well, still not that usable. So can we actually do better? And as I said, we rarely start a proof from scratch. And missing assertions are likely to be similar to assertions that are already in the code base. And especially when we looked at Dafny code base and we actually clustered some assertions, we discovered that most assertions actually have a really similar structure. So there's only few types of assertion that we will write in the code base. They all like some kind of variation, but they all have the same structure. So the idea is like, then let's use this assertion that's already there, form similar lemmas, and provide them to the LLM, because LLMs are well known to work well with examples. And so how does it work? Well, we had the baseline that like around like over 30%. Now we had examples. And actually, we did one thing that was really interesting. We took example assertion from the same code base at random. So completely random, like I think it was like 6 different assertions from the same code base. And it actually works really well. So example assertion from the same code base are beneficial. And you might wonder why. Like random assertion would help. Like as I said, there's only so few type of assertion that actually exist in your code base. So meaning that even if you pick at random, there's a high chance that you will pick an assertion that is similar to the one you need. But we can be smarter. We can actually try to pick the assertion with some kind of similarity based on the context. So now we know that our lemma has a certain structure, like with the if and else like previously, and we know that we have another lemma that has the same structure. And we can use the assertion from this other lemma to, as an example for this new lemma. And that's what we did in the other line here in yellow. And what you see is we get some small improvements. So example assertion from similar contexts are actually better. And since like the similarity metrics now are like quite cheap, it's something that we should use. And finally, now we are above 50%, which I would say like if 1 time out of 2 an LLM can help me write the assertion, I think I would be pretty happy. But when does it fail? So here we have another lemma that like we need to generate this assertion here in infer array 2, and we provide an example. And if you look at the example, the structure is like really similar. And so we say like, okay, we're on good track, an example is similar. And what the LLM generates is actually really close, but if you can spot the difference, it's 1 character away, is like, in this assertion is, in this code base, is infer array 1 and infer array 2. And the LLM doesn't know that because we don't give it the function that are existing because there are too many functions existing. But now, we could think, and we didn't do that, but that's definitely something that could be improved, is like we could add some functions to the context depending on the first answer to LLM, or we could also try to do some program repair. The second example of when does it fail is this other lemma, and what you need to notice here is you see the word flatten everywhere. And if you know how LLM works in terms of probability and token, you will guess that every assertion that is generated uses flatten. But that's not what we want. We want this assertion that x plus ys is equal to ys. And so here, we need to understand, like, at some point, can we ban some element of the assertion to ask the LLM to force the LLM to go through a different path? So finally, we had this first thing of like providing the assertion placeholder to focus on the content of the assertion, then find similar assertion, and we made this into a tool that we call Laurel, and that we generate assertion. But I want to come back on one thing. I talked at first about program verifiers and the proof assistant and automatic verifiers and how AI will change this thing. And I promised that I will answer this. And actually, I lied because I'm not smart enough for that. So I asked my favorite assistant, ChatGPT, and he told me like a bunch of reasons of like what kind of research we should do and what kind of thing we should do. And this is all great. And actually, if you read it, it's not that bad. But what made me happy is that one part of it is, well, what we should do to apply AI to verification is to synthesize assertion. This is an important thing as the AI role. And that made me happy because that's a part of what we did. So thank you.
Thank you. Come in, any question?
Hi there. I was curious with the different models you tried. So I understand there are some LLMs that are fine-tuned for proof engineering. If you experimented with those, compare those to ChatGPT at all?
So this was used with ChatGPT at first 4 and then 4.0. We didn't try with fine-tuned models because at first when we did this, there was no fine-tuned model for Dafny per se. Like most of the ones were like for proof assistants. I think it would increase a bit the success rate, but it will not fundamentally change the problem. Like for example, 4 was not as good as 4.0, but we had the same thing of the location not being great and the example being quite useful. So yeah.
Thank you.
Yeah, thanks for the great talk. So did you use some kind of prompt techniques like chain of thought or something like?
Yes. So a prompt was like we worked on, and like we also tried like chain of thoughts. If you try chain of thoughts, you get a bit better result, especially on the baseline. But like by adding just the location, you get significant improvement no matter what, with or without chain of thoughts.
Okay, thanks.
So to my understanding, your benchmark only contains those functions with fixed lemmas, and your job is to synthesize the assertions in the function, right?
Yes.
So why don't you focus on generating the lemmas instead of the assertions? I think it's a more difficult problem.
So I'm not exactly sure of the question, but I'm going to try to answer it to the best of my abilities. What we did is sort of ablation. We have a lemma or a method that like actually verifies. We remove one assertion, and if this assertion makes the proof fail, then we add it to a benchmark. So the goal for the LLM is to add the assertion that will make the lemma pass. So it is a simple task, but it is a task that needs to be done for the code to prove.
Okay.
Okay, thank you. Let's thank the speaker again.